So, section 12.2 deals with changes of state, and we'd like to discuss or define the heats of vaporization and heats of fusion, as well as calculate temperature changes due to heat transfers. Before we do that, let's do a little bell ringer review. I'll have it on the board there. You can go ahead and pause the video as you try that problem, and then unpause and we'll show you the solution. So what's going on here is I've got a beaker of water, and there happens to be 300 grams of water, and it's currently at 22 degrees Celsius. And then we're adding some silver to it, and that silver is at 80 degrees Celsius. And because it's hotter, it's going to lose its heat. So some of the heat will leave the silver, go to the water, until eventually they're at the same temperature. And that temperature turns out to be 24 degrees. So this 22 will go to 24 degrees, and the block of water will also go to 24 degrees. They're reaching equilibrium. And we just want to figure out how much silver is required for that to happen. Well, this is definitely a heat flow problem. Heat is transferring from the metal to the water, so what I want to do is figure out how much heat is transferring from the metal to the water. And I can find out the amount of heat that the water gains, because I know I have 0.3 kilograms of water, and the specific heat for water is 4180 joules per kilogram Celsius degree, and the temperature change of the water, it goes from 22 up to 24, so final minus initial, 24 minus 22 would give me my change in temperature of 2 degrees. So if I multiply this all out, 0.3 times 4180 times 2 gives me 2,508 joules of heat that the water gained. Well, that's fine, but I want to find out how much silver was required. Well, where did this water get the heat from? Obviously, it came from the silver. So whatever the heat the water gained is how much heat the silver lost. So this Q, this heat that the water gained, is also equal to the amount of heat the silver lost. So I'm going to use the same equation, but now the heat for the silver, Ag, is negative 2508 joules, because it lost that much heat. And I'm going to work backwards. The mass of the silver, I don't know. The specific heat of silver, we can look up in your textbook. The constant is 235 joules per kilogram Celsius degree. And the change in temperature, the final was 24, and it started at 80. So 24 minus 80 gives you a negative temperature change. You have a negative heat there. The negatives will cancel out. So to find out the mass of the silver, just take your 2508 divided by 235, and then divide it again by whatever 24 minus 80 is, and you get 0.19 for your mass. And that has to be in units of kilograms. If you get a negative value, that just means you forgot to make this negative, or you subtracted this the wrong way. You can't have a negative mass. Hopefully you agree with the 0.19. All right, let's look at the new stuff today. Changes of state. Now, when we talk about changes of state, we know there are really 4 of them. We're talking about going from a solid to a liquid to a gas or possibly plasma, which is just heating up the gas even more. We'll focus mostly on these three. And what does a solid actually look like? Well, this is the model we're going to use. Imagine you got these solid particles and they're tied together with springs. Throw some more over here. And the reason we like using the spring analogy is we know even though they're solid, the particles are still moving. So they can vibrate back and forth on each of those red springs. And if you add more and more heat, they vibrate more and more. Eventually, if you add enough energy to get them vibrating so much, they could break. And if those red springs or red bonds break, it turns into a liquid. So increasing the energy leads to an increase in your thermal energy, which will eventually break the spring or break the bonds, and then it becomes a liquid. The point this happens at should be constant for a given substance, and that is called the melting point of that substance. So after all of these springs have broken, you now have particles right next to each other, but they're not locked in a certain position. They're free to roll around each other, and that sounds like you have yourself a liquid. Well, if you keep adding energy, what's going to happen to those liquid particles? Well, obviously they're going to start moving around more and more, and eventually, given enough energy, the bonds that are holding the liquids close together can break, and then it becomes a gas. And this happens at the place where we call the boiling point. Again, that should be a constant for a given substance. We know that ice melts at 0 degrees, and water boils at 100 degrees Celsius. Our first definition talked about, or objective talked about heat of fusion. Heat of fusion is defined as the amount of heat it takes to melt exactly 1 kilogram of a substance. So Q equals M times HF. Heat of fusion is a constant, just like specific heat is a constant. The reason it's M times HF is, obviously, the more mass you have, the more heat it takes to melt it. If you have a small chunk of ice versus a huge cube, it takes more energy to melt the huge cube. This H sub F is a constant. You won't have to memorize it. You can look it up. I'll either have that in a table on your test, or it's found currently on page 287 in your textbook. But that's another way to find Q of a change of state. We know that you can also go from a liquid to a gas, and that's called vaporizing something. The heat of vaporization, or HV, is the amount of heat it takes to vaporize 1 kilogram of a liquid. How would you compare the Q, or the amount of heat to melt something, with the amount of heat to vaporize something? Hopefully you realize it takes a lot more energy to vaporize something than to melt something. If you have 100 grams of ice in a pan and stick it on a stove, it takes a certain amount of energy for that to melt. It doesn't take that long. But if you take that 100 grams of water and try and get it to completely boil and vaporize so there's no water left, it takes a lot more energy. So if you would compare HV, heat of vaporization, with HF, it is higher because it takes more energy to do that. And just for the record, if you're going the opposite direction, if you're going from a gas to a liquid, it's the same magnitude, same number, it's just going to be opposite. So instead of adding heat to melt it, you'd be removing heat, how much heat would be giving off when it goes from a gas back to a liquid, or a liquid back to a solid. So that really is our first objective, define heats of fusion and vaporization. Now I want to talk a little bit about temperature changes due to heat transfers. And to do that, we're going to have what's called a heating curve for water. Your book has an example of one. It should look similar to this. Every pure substance has its own heating curve. And they will look very, very similar to this. A couple things to note. We're talking about water. Well, if the water is below 0 degrees, it's going to be ice. And this is the time as heat is added. So as you add heat, notice the temperature of that ice will rise until it eventually gets to 0. Once you're at 0 degrees, if you continue adding heat, it'll look like you're adding it for another minute and a half, then the ice will melt. Interesting thing is, the temperature does not change during that transformation. Once it's all completely melted, then, as you continue adding heat, it looks like from 2 to 4 minutes, the temperature of the water will rise. In this example, at the 4-minute mark, it took, or once you get to 4 minutes, you now have water at 100 degrees. Well, if you continue adding heat to water at 100, then it will start to boil. As it's boiling, the temperature doesn't change. So notice, from 4 minutes to 8 minutes of continually adding heat, the temperature stays the same. All of the energy that was being put into this water is going to break the bonds that's holding the molecules together. Once all of those bonds break, it becomes steam, or water vapor. And if you continue adding heat after the 8-minute mark, now the temperature of the water vapor can increase. So if you've ever noticed a bag of microwave popcorn, it says the caution is caution when opening the bag, because that steam can actually be over 100 degrees. The water will never get to be over 100 degrees if it's pure water. This chart also kind of shows you why temperature isn't part of those two Q equations. Because while you're changing the state from a solid to a liquid, there is no temperature change. It stayed at 0 degrees when you melted and at 100 degrees when you vaporized it. So let's look at a little problem here. It says, how much heat is needed to raise the 2 kilograms of ice at 253 Kelvin to vapor at 393 Kelvin? Well, what is the temperature in degrees Celsius of 293? Remember, Kelvin is Celsius plus 273. So if I have 393 here, that's Celsius plus 273, or your Celsius temperature for this guy is simply 120 degrees Celsius. For the 253, we have 253 equaling Celsius plus 273, and the Celsius then would be negative 20 degrees for this guy. So on this chart, what we're trying to do is go from here, water at negative 20 degrees, ice at negative 20 degrees, to water at 20 degrees. It seems simple enough, but you can't just use the Q equation and go from negative 20 up to 120, because sometimes we're adding heat and the temperature isn't changing. So really what we have is 5 parts to this problem. We have the part where we have the solid ice Then we have the amount of heat when the ice is melting. Then we have the amount of heat to raise the temperature of the liquid water. Then we have the amount of heat where the water is boiling. And finally, the amount of heat to raise the temperature of the boiling water. So it's really a 5-part problem. And let's start with the first one. In part 1, the temperature is actually changing, which means I'm going to use the Q equals mc delta T equation. So to find the amount of heat for part 1, looks like the first 40 seconds or so, I need the mass, which was 2 kilograms, times the specific heat. Well, the specific heat of ice is different than the specific heat of water. We know water is 4180. If you look up the specific heat of ice, you find it's only 2060. And the temperature change, it goes from negative 20 up to 0, so it changes by 20 degrees Celsius. So our Q1, when you multiply that together, 2 times 2060 times 20 gives me 82,400 joules. And that is simply the amount of heat needed to go from negative 20 up to 0. Once we're at ice at 0, we need to actually melt the ice. So to find Q2, that's going to have to be the heat of fusion equation, the amount of heat to melt something. Well, the mass hasn't changed. That is still 2 kilograms. The heat of fusion, from your table in your book, table 12.2, is 3.34 times 10 to the 5th. And when you multiply that together for Q2, you get 6.68 times 10 to the 5th joules. So that brings me right here. I've now raised the temperature of the ice, and I've now melted all the ice. We're at the 2-minute mark. If we continue to add heat, it's going to melt the ice. It's going to raise the temperature of the water. We just have melted the ice. So now I want to find Q3, which goes from 2 minutes up to 4 minutes, or mc delta T. The mass is still 2. Take that times the specific heat of water, because now I'm just raising the temperature of water, 4180. And my temperature is changing by 100 degrees. It's going from 0 up to 100. So 2 times 4.18, just kidding, 4180 times 100 equals another 836,000 joules. That is simply the Q3. That is how much it takes to raise the temperature of the water up to the boiling point. We are now up to here. At this point, we just need to change it from liquid water at 100 to steam at 100. So that sounds like a change of state again. So Q4 is m times heat of vaporization. The mass is still the same, doesn't matter what state it's in. The heat of vaporization of water is 2.26 times 10 to the 6th. When you multiply that together, we get 4.52 times 10 to the 6th joules. And that brings us to this point. That's how much heat it took to actually boil the water. And lastly, we just need to raise the temperature of my steam to go from 100 degrees to steam at 120. So since the temperature is changing, you need to use the Q equals mc delta T equation. The mass is still 2, specific heat of steam is different than that of ice. It is 2020. And if I'm going from 120 degrees to 100 degrees, my temperature changed by 20. If you multiply these together, 2 times 2020 times 20, we get 80,800 joules. So to answer this question, how much heat is needed to raise 2 kilograms of ice from negative 20 degrees Celsius to 120 degrees Celsius, you would have to take Q1 plus Q2 plus Q3 plus Q4 plus Q5 to give me my total amount of heat necessary. And when you add those together, 82,400 plus 6.68 times 10 to the 5th plus 836,000 plus 4.52 times 10 to the 6th plus 80,800, I get, and it looks like we have, well, it should only be one significant digit according to the problem, but I'm going to leave it as, I'm going to go to 3. Q total, calculator gives you 6,187,200 joules. And again, if you wanted to round to only one significant digit, that would be 6 times 10 to the 6th joules of heat for this process. So when you're solving these problems, you need to figure out exactly where you are on this graph, and if you're going through a change of state, remember to calculate the energy to change that state along with the energy to raise the temperature later on. And remember that specific heat of ice is different from water or steam.